This video is part of a course on food physics, of which this is the theory section. In this subsection, we talk about boundary conditions that are part of the description of the single phase transport processes. The immediately following video will summarize the single phase transport equations, that's the governing equations and boundary conditions. Now here in this little section on boundary condition, we only discuss the simplest versions of the boundary conditions and note obvious limitations at the end when we try to use it for food processes. Why do we need boundary conditions? Well, boundary conditions are needed from physical as well as mathematical reasons that I will illustrate using two simple examples. First, physical reasoning. So physical reasoning, let's say we have this domain where the governing equation really applies inside the domain, whereas the boundary condition applies on the boundary. Now you can see that the inside is certainly affected by what's going on at the boundary. A good example would be if we put on a jacket on that changing the outside boundary condition, we feel warmer inside. So the inside is affected by the boundary. So that's the physical reasoning. And then for mathematical reasoning, I want to bring this simple example of heat transfer in a slab. So let's say this is hot and this is cold, and it's in a slab. So my equation describing heat transfer is given by d squared t dx squared is equal to 0. If we solve it, dt dx equal to c1, so then t is equal to t1x plus c2, where is the c1 and c2 are constants of integration. So they need to be found. Yes, we have a solution, but that is a general solution. It is not specific to the problem. This simply says that the temperature will vary linearly. Whether it's going to be this one or this one depends on the boundary conditions. So we have physical reasoning as well as mathematical reasoning that we absolutely need the boundary conditions. Now, a few general comments about boundary conditions. First, of course, we just said it's trivial that they are conditions at the boundary, not inside. They are needed to solve the governing equation for a specific situation, again already mentioned. Then we have to find out which one applies at a specific boundary from a list of the simple boundary conditions that we're going to talk about next. Then the other part is we have to choose exactly one from the list on one boundary. We cannot apply two different boundary conditions simultaneously on the same boundary. Then we need two boundary conditions for each spatial variable, and a simple way to see, like I showed in the previous slide, so if you have heat equation that is second order, let's say steady state in a slab, so we have d squared t dx squared equal to 0. If we solve it, we get t equal to c1x plus c2. So there are two unknowns, and so we need two conditions. So we need two for each spatial variable. So if we have also, if we have, let's say it's 2d d squared t plus d square t plus dx square plus y square equal to 0, Then we need one set for x and one set for y. And then, of course, we need initial condition when the problem is transient. So it's also a function of time. How many boundary conditions are there? Well, there are many, but most of the time we talk about three different types of boundary condition. One is where the boundary value is known, meaning let's say temperature is known at the boundary. Other one is the flux is known, and the third one is convection. And so they have their mathematical name. So this is called Dirichlet boundary condition, and this is Neumann, and this is Robin's condition. And so these are the three types that we'll be talking about now in the context of heat transfer and mass transfer. The boundary conditions are not some sort of a fictitious mathematical manipulation. The boundary conditions very much have to relate to the reality and what can be maintained at the boundary, what we can actually enforce on the boundary, that decides the boundary condition. So it's closely tied to the physics. Let's look at the three types of boundary conditions that we just mentioned in the context of heat transfer. So choosing some food process situation. So let's say we have steam condensing in canning. So this is a can, and steam is condensing in here. So condensing steam can maintain, because of the phase change process, it can really maintain close to the steam temperature. And therefore, the condition here on the surface can be maintained the steam temperature, and so then this is always that steam temperature. So we write the boundary condition T at x equal to 0. Now I am not getting into what shape of the can or which surface of the can. X equal to 0 simply signifies the boundary. So at the boundary I can maintain this physically. I need you to really see this. This is not something that we just assume to solve a problem, but it is a physical reality. Likewise, for the second type of boundary condition, if we have, let's say, infrared radiation, like from a grill inside a toaster oven or a toaster, infrared radiation, it has those elements that are heated, and when heated they are giving out radiative flux. It doesn't matter if your toast is completely burned, it will still give out that same flux. So then we have a condition where heat flux is given at some value. So in other words, here the temperature is not set. In fact, if the temperature will continuously increase with time, but the flux, the amount of energy coming in, is set, and so here is a condition where heat flux is given, and so we write flux. So this is the amount that is coming to the surface, and that's what is getting inside. So because it's getting inside by conduction, it's using Fourier's law that we talked earlier, minus k del t del x at x equal to 0, the flux is equal to the value that is coming from physical consideration. Then the third one is the convective boundary condition. And so here, let's say we have a oven with a hot air blowing over the food. So if the hot air is blowing over the food, it cannot really maintain the temperature the same way as it was for steam, for example, and neither can it maintain a constant flux. So the condition simply says that whatever is coming out of the solid from inside should be equal to what is leaving outside, meaning if you think of a line that has no mass, then what's coming from the left should be equal to what's leaving the right. I realize that the picture here is for a cooling problem, so if it's heating, it's going to look something like this, but the same idea, that what's coming in is equal, what's from the right is equal to what's from the left. So the two fluxes should be equal. So the condition simply says that. So this is the flux inside is equal to the flux outside. Conductive flux equal to the convective flux, and these are sort of the quantities that define what is convection. So this is my H value and this is the surrounding temperature T infinity. Okay, so then we talked about three different types of boundary conditions for heat transfer, the most common one, but relating each one to physical situations. Now we do the same for mass transfer. It's completely analogous or almost completely analogous. I'll mention when there is a bit of a difference. Okay, so the first one is instead of temperature given on the surface, we have some concentration given on the surface. So let's say we are drawing with a very high air velocity. So if it's drawing with very high air velocity, it can maintain the surface at the condition in equilibrium with the air, which means it can always maintain that surface condition. And so the surface condition is therefore a constant. So concentration of A, so let's say A could be moisture at the surface, is equal to some set value. So value given at the surface is the first kind of boundary condition. Then the second kind, just like in heat transfer, we have flux given. Now it's hard to really enforce some sort of a mass flux in this context, and so the two that the two sort of extreme cases that we can enforce are when flux equal to 0, as in this chocolate bar. If you put aluminum foil over it, then you're making no moisture leave, so the moisture flux is equal to 0. So the mass flux given is equal to 0. So 0 is a special case. It is still flux given, but it's flux equal to 0. And we write the boundary condition as concentration gradient is equal to 0. Another case, again, this same condition, but another special situation is when we have symmetry. So let's say we have a slab and it's drawing from both sides. So the profile is going to be symmetric. So if it is symmetric, then the condition at in the center is going to be del Ca del x equal to 0, or flux equal to 0. So flux equal to 0 is still flux specified, but it's kind of a special situation. But that's the one that is used most often in mass transfer. And then the final one, again analogous to heat transfer. So let's say hot air is blowing over the surface, but maybe not as high air velocity. In that case, we do not know what is the concentration of, let's say, water at the surface, and we also do not know what is the flux. So neither one nor two will work. So what we will say is, look, I don't know what is going on in terms of such detail, but what I can say is moisture coming from the left should be equal to moisture leaving the surface, because it's a surface, so there's no other place to go. And so diffusion from inside to the surface is equal to convection on the surface. And so we're going to write the condition this way. So we say diffusion from inside, diffusivity of water in the solid times the concentration gradient. So this is my Fick's law. Inside the surface, so in the solid, and that is what's coming to the surface, and then what is removed from the surface is given by the convective mass transfer formula. So this is my HM, mass transfer coefficient, times condition at the surface and condition at infinity of the moisture. But now I'll break down the moisture into more detail, and this is where heat transfer and mass transfer are not exactly the same, because we need to consider something else. And so let's look at this. Inside, when we are talking about diffusion, it's diffusion of water inside, or it can be diffusion of water inside. And so because it's, or let's even say water and vapor together, so it's moisture inside, but it's moisture in the solid, whereas outside it's moisture in the air. So this is solid and this is air. So outside is moisture in the air. These are not the same quantities. They are related. So at the surface, the inside in the solid is related to in the air outside. This relationship is there. But the point is they are not the same. So on the left hand side, the variable is, for example, concentration of water in the solid. On the other side, on the other hand, is concentration of vapor in the air. So we need additional relations so that these two variables can be linked. And that comes from the isotherms, from the water activity relations. But we need that relation to really use this equation. Otherwise, this equation has two different variables on the two sides. That is a different from heat transfer. So in heat transfer, these 2 points, the outside moisture profile can look like this, right? Dry air here, and so it will be more moist near the solid because moisture is coming out. So the outside profile would look like this, and inside profile, because it's drying, it looks like this. So the outside and inside do not meet. But in case of heat transfer, they meet. There's only one temperature on the surface. So that's why these two are different, but nevertheless, same idea. Now we have a shorter slide talking about boundary conditions for fluid flow. We're only going to talk about the most common version, which is a value given. So if you have fluid flowing in a container, so let's say this glass container, this glass jar is used in canning, so we close the lid and we heat up. So now the fluid inside will move. Okay, so in order to describe the fluid movement, we need boundary conditions. And so the boundary conditions, uh, and this is a schematic of its actual values for one set of conditions of how the velocity profile look. So on the very surface of this glass, fluid is stuck to the glass surface. So the fluid moving over a solid surface has a velocity of 0. That is the most common assumption, and it works for almost all of the time. So velocity is 0, and and then of course it increases inside as fluid can flow up, but on the boundary is what we are interested. So the fluid flow on the solid surface is 0, so we write the boundary condition velocity, in this case at the radial location r, velocity at r equal to r is 0. And this is the most common one, and we, instead of getting into the more complex boundary conditions which are very much used also in food, we will stop here because we're not trying to cover all different complex situations, and therefore we'll stop at this most common fluid boundary condition, which is it's also called no slip. So there is 0 velocity on the surface. We discussed boundary conditions, the most common types for heat transfer, mass transfer, and fluid flow. Before we conclude this section on boundary conditions, I want to also share how trying to apply those for food, there's going to be challenges, there's going to be limitations, and I share this using the example of heat transfer. So let's say we are cooking meat, we are grilling meat. So you must have noticed sometimes water accumulates in there. And so all of those things we have to include. Now the equations we derived are for single phase. And so in a system like the one shown in the picture, it's going to be very hard to handle using single phase. So later we discuss again boundary conditions but for multi-phase transport situations with heat transfer, mass transfer, and flow, and this is a separate module on boundary conditions under porous media. I just want to bring up a little bit of the concepts here to make the point. So there we have to think of the meat as made up of these phases, the solid, water, vapor, and air. And so let's say this is my boundary. Okay, so there is the inside and then there is the outside. Okay, and so for heat transfer, let's say what are the boundary conditions? So conduction in the solid is equal to convection. That part is exactly the same. That's what we just derived. But we write that for the solid phase. for the liquid phase, and I just choose one of them, that is water. So water can diffuse to the surface, and then we can think of what is going to happen to that water. So there are two possibilities we can think of. And this is when things are not blowing, and I'll explain blowing in a second. So if it's non-blowing, then water comes to the surface and then it evaporates. So that's a different situation. And then another situation would be there's no evaporation. Water just accumulates. As I mentioned, we see when we are grilling meat. So the diffused water on the outside can have these two possibilities outside of the boundary. The other interesting part, and this is why I wanted to show this slide, if the pressures inside are high, then the fluid can ooze out, can just blow out, okay? And that is so it just leaves as liquid. It doesn't necessarily accumulate there. It doesn't evaporate. It just leaves as liquid. So those things are real, and those things need to be handled. The most important thought I want to leave you with is that the boundary conditions here for single phase are still the building blocks, are still the ones that are used to develop boundary conditions in such complex situations. So these are the most basic and most important ones of the boundary conditions.